Hey, it's me again, Mark Lester, and for today's video, I'll be talking about the most stable conformation of 1-methyl cyclohexane. Unlike in any other single-bonded hydrocarbons, the carbon atoms of a cyclohexane are arranged in such a way that the molecule will not experience any angle strain nor torsional strain. This is because all neighboring CH bonds are staggered and the CCC bond angles measure exactly 111.5 degrees, which is very close to the ideal 109-degree tetrahedral angle. This conformation is called chair conformation as it resembles a lounge chair having a back seat and a footrest. One of the interesting properties of a chair conformation is that the substituent in a cyclohexane ring can be positioned in two different ways: the axial position and the equatorial position. In axial position, the substituents are positioned perpendicular to the ring or parallel to the ring axis. Meanwhile, in equatorial position, the substituents are arranged in a band around the ring equator. So now, let's take a look on the structure and the most stable conformation of 1-methyl cyclohexane. I have here a ball and stick representation of a 1-methyl cyclohexane molecule. The blue balls herein correspond to carbon atoms, while the hydrogen atoms are represented by the orange balls. As you can see, the methyl group attached to the cyclohexane ring is in equatorial position. This is the most stable conformation of 1-methyl cyclohexane. Hence, this must mean that the equatorial conformation is of lower energy compared to the axial conformation, since higher energy equates to less stability. As a matter of fact, when the methyl group is in axial position, this is 7.6 kJ per mole higher in energy than in equatorial position. But why might that be? Let us try to rotate the methyl group 90 degrees clockwise, so that the methyl group will be in axial position. The energy in equatorial and axial conformation are significantly different because of the steric strain brought by one through the axial interactions between the axial hydrogen atoms and methyl group in axial conformation. When both are in axial position, the neighboring hydrogen atoms in methyl group are too close to each other, resulting to steric strain. But when the methyl group is in equatorial position, no interaction between the methyl group and neighboring hydrogen atoms takes place. Overall, equatorial conformation is more stable than axial conformation by 7.6 kJ per mole because in equatorial conformation, there is no 1,3 diaxial interaction between the axial methyl group and axial hydrogens in carbon 3 and carbon 5, producing no static strain.